Introduction to Statistics, Chapter 7, The Normal Probability Distribution, Section 7.1, Properties of the Normal Distribution. A probability density function, or PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. Number one, the total area under the curve of the equation over all possible values of the random variable must equal 1. 2. The height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. This implies that any two intervals of equal length are equally likely. The graph of a uniform distribution results in a rectangular shape. Okay, let's look at an example. The reaction time x in minutes of a certain chemical process follows a uniform probability distribution with x greater than or equal to 5, less than or equal to 10. So first we would draw our horizontal axis, draw our vertical axis, draw a rectangle. The rectangle is going to go from 5 to 10. Now the total area inside the rectangle is going to equal 1. Now, how does this split up for the height? That's the next thing we want to do is get the height of the rectangle. Well, the height of the rectangle is going to equal the probability of each outcome within. So if we look at this, we're going from 5 to 10. So if we're going from 5 to 10 in minutes, we could have 6 minutes, 7 minutes, 8 minutes, 9 minutes, and then 10 minutes. So this splits our region into 5 equal parts, which means the probability of each part is going to be 1/5. And since the probability of each part is 1/5, the height of our rectangle will be 1/5. Now, if I was going to go from 1 to 30, okay, then my height would be 1/30, because there would be 30 individual sections, each one 1/30. Okay, this is how you draw the density curve for a uniform distribution. Question B, what is the probability the reaction time is between 6 and 8 minutes? Well, we look at our curve. Okay, we want the probability x is greater than or equal to 6, less than or equal to 8. We look at the curve. Here's the curve. Where do I want? I want from 6 to 8. So what would this be? This would be 2 times 1/5, which equals 2/5. You'd have 2 of the regions, because 8 minus 6 is 2. Now, what if I want the probability the reaction time is at most 8 minutes? Now we have to understand what at most 8 minutes means. Well, that means the probability x is less than or equal to 8. So we have our curve. Now I want it less than or equal to 8, so I want everything down here, which turns out to be 3 of the sections. So 3 times 1/5 is 3/5. What is the probability the reaction time is at least 7 minutes? What's at least mean? At least means 7 or more. So probability x is greater than or equal to 7. So we look at our graph. We look at greater than or equal to 7. It's going to go 7 to 10, which is 3 of the sections. So it's 3 times 1/5, or 3/5. All right, properties of the normal density curve. The normal curve is symmetric about its mean, mu. Because mean equals median equals mode, the normal curve has a single peak, and the highest point occurs at x equals mu, or the mean. The normal curve has inflection points at mu minus sigma and mu plus sigma. This is the mean minus a standard deviation, the mean plus 1 standard deviation. The area under the curve is equal to 1. The area under the normal curve to the right of mu equals the area under the curve to the left of mu, which equals 0.5. This is because it's symmetric. As x increases without bound, the graph approaches but never reaches the horizontal axis. As x decreases without bound, the graph approaches but never reaches the horizontal axis. Now, let's look at one. Here's a situation of a normal curve. You see mu is in the center, and that's the highest point of the curve. Now, if I take mu minus 1 standard deviation, I take the mean plus 1 standard deviation, bring dotted lines straight up, Those are the inflection points. Now, what is an inflection point? An inflection point is where the curve changes directions. Now, if I take my cursor here, down here, I'm coming up, curving up. When I get to this point, now my curve is going to change directions and go the other way. It's going to start curving down. So these are the inflection points. So every normal curve has two inflection points. Now, graph of normal curve with mu equals 6 and sigma equals 2. Well, we would draw the normal curve. 6 would be in the center. We'd come out 2 to the right, 2 to the left, 2 to the right, 2 more to the left, 2 more to the right, 2 more to the left. This would be the normal curve for mu equals 6 with a standard deviation of 2. Now, what if the mean was 6 and the standard deviation was 1? How's that going to change the graph? Well, 6 will be the center, but now we're going by ones. There's 8, there's 4, 10, 2, 12, 0. You notice it brought all the data in closer to 6 and pushed it up. So the smaller the standard deviation, the more compact the graph is, and it goes higher. The larger the standard deviation, the more spread out the data is. Now, we talked about the empirical rule in an earlier chapter. The empirical rule goes with the normal distribution. What the empirical rule states is that within one standard deviation of the mean, there's 68% of the data, or 34% to the left, 34% to the right. Within 2 standard deviations, if I would go down 2 standard deviations, go up 2 standard deviations, that will contain 95% of the data values. 2 standard deviations within the mean. And if I go out another standard deviation, go 3 standard deviations to the left, 3 standard deviations to the right, now I have 99.7% of the data within 3 standard. So that only leaves 0.3% on the outside. So if you take 0.3 and divide it by 2, you get 0.15% on the right tail and 0.15% on the left tail. This is just an illustration of the empirical rule. Now, in the following graph, determine the mean mu and the standard deviation sigma. Okay, so if I look at this graph, what would the mean be? Well, the mean would be 5, and the standard deviation would be 2, because I'm going 5 to 7, 5 to 3. I'm going by 2s. Okay, the inflection points for the graph. The inflection points would be 3 and 7, 1 standard deviation from the mean. Now, what about this one? What would the mean be? Well, the mean would be 530. Standard deviation from 530 to 630, from 630 to 730, 730 to 830. The difference is always 100, so the standard deviation is 100. And the inflection points for this graph would be at 430 and 630. 1 standard deviation to the left of the mean, 1 standard deviation to the right. Okay, now if you were asked to draw the normal curve with a mean of 35 and a standard deviation of 5, how would you go about it? First, you would draw a bell-shaped curve, and you would put a dotted line down the center for the mean. Then you would put at least 3 dotted lines to the right, 3 to the left for the standard deviations. In this case, 35 would go in the center. I would add 5 to 35 to get 40 for 1 standard deviation to the right. Subtract 5 to get 30, 1 standard deviation to the left. Add 5 to 40 to go out another standard deviation, 45. Subtract 5, 25. Add 5, 50. Subtract 5, 20. And this would be the graph of a curve with a mean of 35, standard deviation of 5, if it was normally distributed. Now, what about where the mean is 215, standard deviation is 30? Well, again, you just draw the bell-shaped curve with the mean in the center and standard deviations 3 each way. So 215 would be in the center. Add 30, 245. Subtract 30, 185. Keep adding 30, 275, subtract 30, 155. Add 30, 305, subtract 30, 125. This would be the normal curve of mu equals 215, sigma equals 30. Okay, now a histogram indicates that a normal distribution could be used as a model for the variable if the shape of the histogram takes on the shape of a normal curve as illustrated below. When we talked about histograms earlier, we talked about a histogram could be skewed left, skewed right, could be uniform, or it could be symmetric. So basically, if it's going to fit the normal distribution, the histogram is going to follow a symmetric format. So if you look at this histogram below, the height of 3-year-old females, yes, I could possibly graph a normal distribution curve over top of the graph. It's not going to be exact, but it's close enough to say that it would follow a normal distribution. Now, some examples that would not follow the normal distribution. Well, look at these examples. Waiting time for the American Eagle roller coaster. Okay, if you recall, this would be a skewed right histogram. It does not take on the shape of a normal distribution. And length of phone calls, again, skewed right. Interpreting the area under a normal curve. Your author uses two interpretations. Okay, let's look. If the life of a refrigerator is normally distributed with a mean of 14 years and a standard deviation of 2.5 years, and the area under the normal curve to the right of x equals 17 is 0.1151, provide two interpretations of this result. Okay, first, this would mean the probability that a randomly selected refrigerator is more than 17 years old is 0.1151, or you could represent it as percent, 11.51%. So he's going to use probability as one of his interpretations. His other interpretation is going to use proportion. The proportion of refrigerators that are kept more than 17 years is 0.1151 or 11.51%. So the area under the curve would give you the probability or the proportion. So there's two ways to look at and interpret the answer as we go further into the chapter. Okay, so those are the two interpretations your author uses, probability and proportion. All right, this brings us to the end of section 7.1.